Hey guys, welcome to PyCon Hyderabad 2020. This is your host Vijay. Today I'll be hosting this keynote, and along with me is Prabhu Ramachandran. And before we get started, I just wanted to let you know that all the questions which you have, you can either use the Q&A feature or the feed feature towards your right, and you can ask your questions there. Prabhu will be replying to your questions in the chat. Also, at the end of the session, Prabhu will be available for any Q&A. So feel free to either ask your questions in the chat or at the end. Thank you. And get started with this keynote. Today we have Prabhu Ramchandran, who's gonna talk a little bit about Compile. But before that, a little bit about Prabhu Ramchandran. So Prabhu is currently a faculty member at the Department of Aerospace Engineering, IIT Bombay. His main research centers around scientific computing and data visualization, and a little bit of high performance computing as well. He's mainly known for being the creator of the Mayavi Python package for 3D visualization. You can check it out in the link which I'll be sharing in the feed. And today he's going to talk about Compile. So let's get started. And again, feel free to uh, ask your questions in the feed, as well as you can raise your hands, and Prabhu will be replying to you. Thank you.
Hi everyone, I'm Prabhu Ramachandran. I'm from the Department of Aerospace Engineering at IIT Bombay. I'm going to talk to you about a package called Compile, which I've been building with my students, which allows you to do high performance computing with Python. I'm really grateful to the organizers for having called me to this conference and asking me to keynote, especially Ramanathan, who's a good friend. Thank you, for inviting me here. I'm really grateful to IIT Bombay. This is a campus, picture of the campus. We have a hill on the campus and a lake. It's a beautiful campus, and they provide for an excellent academic environment, which has facilitated my work over all these years. Grateful to them. So before we begin, I'd like to thank one of my students, Aditya Bhosle. He was a dual degree student, and he did an outstanding job. He's a brilliant student. He did a lot of the work that I'm going to be presenting today. So I'm really grateful, lucky to have had him as a student. Okay, so a little bit about me. I've been developing open source software, especially in the context of scientific computing Python for many years. Well known for the package called Mayavi, the 3D visualization software package. But in addition to that, I've also been working with my students on an open source computational fluid dynamics kind of package called PySPH. And then the package I'm going to talk about to you today, as well as several other packages, including something called Yaksh, which is an online course hosting and testing platform, which you may be interested in. I've also been fortunate to be associated with the FOSSEE project, of which I am a co-PI. And for many years, we've been trying to promote the adoption of open source software in education in India. And this is funded by MHRD, this particular project. So I've been really fortunate to be associated with this project as well. My research itself focuses on computational fluid mechanics. But I look at a non-mainstream approach where we use particles in order to simulate various things. So for example, here's a picture of a boat, and this is an animation of a boat, and there's like water that's going to splash, and you're going to see basically this boat moving around. These are all done computationally. This is just a sample computation, but you can see the wave structure, how the boat interacts and things like that. But we can also do things like structural mechanics problems with this, and all of these are done with the open source tools that we built in our lab. And this is all done with PySPH. So these are two steel rings that are colliding, and basically this is looking at the deformation of these rings in time. We can also do simulations like this, where you have some water essentially impacting a bunch of objects and how they all interact. And this can also be rendered very prettily using ray traced rendering. But this is the kind of research I look at. So what I'm going to do today is I'm going to talk to you about a problem that is very related to the computational research that I do, And there's a reason for me picking this problem. It's simple, easy to understand. But if you understand how to solve this problem, you can actually apply these techniques to a variety of other areas as well. So I won't get into those details, but the idea is I'm going to introduce a simple problem that's very easy for you to understand. And then I'm going to basically dive into parallel computing with Python using the tools that we're building. So we'll come up with a simple solution for it, and then we'll take a more sophisticated approach. And depending on how much time we have, we'll explore what we are able to. So let's look at the problem. So what we're going to look at is a molecular dynamics simulation. What this entails is you have a bunch of molecules or atoms, and these are all particles. So each is an individual atom, and each atom or particle, so we'll just call it a particle for now. Each particle interacts with all other particles using a Lennard-Jones potential. So the potential function, so this is like a potential field, and if you have two particles which are separated by a distance r, there are two parameters of this. One is sigma, the other is epsilon. So depending on the nature of the problem, these parameters will change. But the force, the potential is given by this function. Okay, and if you take the gradient of this, you get the force. And so the force of the jth particle on the ith particle is given by this expression. Okay, 24 by r squared, 2 sigma by rij to the power 12 minus sigma by rij to the power 6 into rij the vector. So this is a vectorial quantity. So we're going to use this in 2 dimensions. And if you're really interested in learning more about this, this particular problem, there's a really nice paper by Daniel Schroeder, Interactive Molecular Dynamics, that you should definitely check out, because it gives you a lot of example problems that you can solve with this simple toy problem we're setting up. Now the potential function that I just described here, actually if you plot it, it looks like this. This is the blue curve, this is the potential. So you see that basically as you approach the origin, the x-axis is basically the radius, r. Okay, so as you come towards the origin, it blows up. The potential function blows up, and this red line is the force magnitude. Okay, and you see that essentially what this is saying is, if the particles start coming too close, there's going to be a very large positive force that pushes them apart. On the other hand, if you look at this, the red line between say 1.2 and 3, the value is actually negative. So it tends to pull particles that are further away, but if they come too close, it pushes them away. So this is the kind of potential, and this is actually designed to model real molecules. Okay, this Lennard-Jones potential, and in this particular case, I'm looking at sigma and epsilon equal to 1. Okay, so this should give you a sense of what's going on in this situation. Now, please note that if the particles are further away by 3 units, right, 3, if Rij is greater than 3, the force is 0. Okay, so we're going to use that to simplify things. So now we'll set up a simple 2-dimensional problem of particles in a box, and this is a rigid box. So look at this box here, this is rigid, and these are some particles. I just color coded them for simplicity, and they're contained in this box. So if a particle moves out of this, it's reflected back. Same way for all 4 walls. And we've designed this to be in such a fashion that you can scale the number of particles, which means I can jack up the number of particles. And this is important because I want to look at how this problem scales when I implement it in different ways. We're going to use natural units where we have sigma equal to epsilon equal to mass of the particle equal to the Boltzmann's constant equal to 1. And this is a natural system of units, and if you have any doubts about this, go back and should read this paper a little bit. It will give you some context about why this is meaningful and things like that. So we're not quite interested in the physics here. What we want to do is we want to be able to solve this problem. Now, so what do we have here? We have these particles. Each particle influences all other particles, right? So now, based on this interaction, you get a force. So every particle interacts with all. So if I have particle I, it interacts with all of the other n particles, and there's a net force. Once you have a force, you can integrate this system to find the velocity and the position. Okay, so we need to do an integration, numerical integration in time, and so if you have x being a position, v being a velocity, and a being an acceleration, and delta t being your time step, right? So which means if you have a set of particles at a given time level n, so there's xi to the power n, the n denotes a time level, I denotes an ith particle. Okay, so we're saying that the ith particle at time level n plus 1 is simply at time position at time level n plus the velocity times delta t plus half times the acceleration at n into delta t squared. Okay, so this is very straightforward. basic, 8th standard physics or something like that. And then we update the velocity to a intermediate state, which with half the acceleration. And once we do this, we actually compute the forces, right? The forces between these particles. And then we update the velocities. Okay, I hope the algorithm is clear. So it's very simple. Find the forces, integrate it in time. These particles will all start moving around. And once they start moving around, you've basically done performance simulation. Okay. So now what we'll do is we'll switch to a live demonstration of this particular problem. So what I've done is, this problem is a bit complicated. So what I'm going to do is, I'm going to basically make this, I've already written out the skeleton, and writing the boilerplate takes a bit of time, so I'm going to make life easier. So I've just made an argument parser, which has the following arguments. Minus n gives us the number of particles, so I can change that. I can change the total time for which it's integrated. The default is 20. We have 200 particles by default. We can also make a plot. If you say minus minus show, it will basically make a plot. And you can have a frequency at which you're going to show the plot, update the plot. Then we pass the arguments. We create this object called the MD, molecular dynamics. Pass all of these passed arguments, set a timer, and then basically call the solve method. So now let's quickly look at how this MD class looks. So it just takes all the parameters, it initializes itself. Okay, and this initialize method is very simple. All it does is it sets up the domain, this box, creates all the particles at the bottom, creates the red colored particles on the top, right? And then it sets the velocity of the top fellow to move downwards. So that thing is moving downwards, it's going to hit these and it's going to start attracting. Then if you see, there's a method called solve, and the solve basically just does the following. If we asked it to show, we'll show the initial setup, and then we'll compute the force. Then while t is less than tf, t is set to 0 here, we basically integrate the step 1. If you remember, the step 1 is basically, this is step 1. Then it computes accelerations and then performs step 2. Okay. So that's it. Update time and then show plot again. And this plot function just does a couple of scatter plots and makes it convenient to show. That's it. It's very simple. That's the skeleton. Okay. Now we need to implement these force functions. Okay. So what we're going to do is, I need to now write for I in range n, for j in range n. Right. So if I equal to j, two particles are on top of each other, that's going to blow up. So you just say continue. Right. Otherwise, we find xij equals x of I minus x of j, y ij equals y of I minus y of j, and then we find rij2 is xij star xij plus yij star yij. So let's go back and look at the formula that we had. This is the formula. We need the force 24 by r squared into this. So let's write that out. So now we need to do a small thing. We can do a small optimization. So if we say if rij2 is greater than 9.0, right? If it's greater than 3 rij square root, I'm not taking a square root, we don't need to do this computation because the force is actually 0. Okay. So now I'll calculate this quantity q2 is 1.0 divided by rij2. This is essentially q squared. Q to the 6 will be q2 times q2 times q2. And now I can say the basic force is 24 into q2 into q6 into 2.0 star q6 minus 1. This is the actual force, and Fx is simply, I just increment this force plus equal to F times xij Fy plus equals F star yij. Right? That's it. So now we have computed the forces. Let's now write the step 1. Y in range n. So now we need to update x. So x of I plus equal to u star pt plus 0.5 star fx I
start dt, start dt. Same way for y. I'm going to be lazy. Let's do this quickly. And now we need to update the velocities as well. So u I plus equals to half fx start it, and vi plus equal to. Okay, so this is now step 1. Step 2 is very similar. Let's do this, and I can just cut paste this code. Oops. I've already implemented the boundary condition because it's a bit tricky. Again, all we do here is we say for I in range n, x is x. If basically the point crosses the right boundary, you pull it back in and you flip the velocity. If it crosses the upper boundary, pull it back in, flip the vertical velocity. Same thing for the bottom and the left side walls. Alright, so it's fairly straightforward. I just wrote it out here. So now we're basically done. In principle, I should be able to just run this. So let's try that. Python demo.py. Sure. Fingers crossed. Let's hope that works. Ooh. So, I made a mistake here. So this should be. Fortunately, if this was truly live coding, you guys would have helped me with this. But since I'm not around. All right. So now it's moving, which is great, but it's going to take a long while. It's going to take a long time. Okay. So we let this continue. So what we want to do now is, now that you have a working model, it's doing something, right? These particles are starting to interact. We're going to start moving around, and it's going to deform and stuff. Okay? So I'm going to just put an end to this, and now what I want to do is optimize this. Okay, so let's go back. So it works, right? But what we want to do is we want to make it a little faster. So we'll do the first simplest thing that possibly works, and that is, so let's make a copy of this. Demo. Okay, so I'm going to just make a. I'm now going to optimize this as I just run this same problem without showing anything. So let it just run for a little while as I do this program. Alright, so we'll see how long it takes to finish this as I quickly use Numba. And all of you must have heard of Numba. It's an amazing package. From Numba, import njit. Okay, and now with Numba, the awesome thing is I can just say njit of this compute force. In fact, the compute force is probably going to be the most slow function in this particular case. Okay, so technically all I need to do is update that. I just need to jit that one function, but I'm going to do it for all of these, and then we'll see no other changes are necessary at this point, so everything else is fine. I hope that's okay. All we've done is we've basically done it's going to take a while. Oh, it's finished. Okay, so it took 52 seconds to finish our previous unoptimized version. Now what I'm going to do is I'm going to run the same thing with Numba. I'm going to show it, and you'll actually see the massive difference. Notice that it's visibly interacting at a much faster rate. Okay, and it's done. And it finished with the plotting. So if I don't do the plotting, notice how long it takes. It will finish in less than a second. Okay, so about 0.8575 seconds as against 52 seconds. So it's about 60 times faster than our naive implementation. If you look at a diff, we just added these 1, 2, 3, 4, 5 lines. That's it. Okay, and that's the amazing benefit we get. Okay, so this talk is not about Numba, right? Otherwise, I'd have titled this talk about Numba. So Numba is awesome, right? But the problem is it's a bit too awesome. Okay, and if you notice the way I wrote my code, I wrote it in a particular structure in a particular form, and that
That was not, by accident. That was by design. Okay? The problem with Numba is it actually allows you to do a lot, and it even supports Python objects in many cases. So which means it tends to be highly forgiving. So you can write pretty poorly performant code and it will still work, and you may not get as great performance, right? I have now tuned my code so that it actually fairly performs with Numba. Okay? So if you want to get optimal performance, you actually need to do a bunch of things. And you notice the way I've written my code, I didn't create any objects in any of those ngtit functions, right? Those functions just took existing NumPy arrays and they just operated on those and did some calculations, right? We didn't use any SciPy or NumPy inside those ngtit functions, and that is a crucial aspect. Okay? So for example, very often you'll write a function and you'll start returning a tuple or a list or do something like that. Those are terrible things to do because your performance will go for a toss. So the problem is if you actually gave that code to Numba, it'll actually try its best to optimize it and make it work. And this is really not a good idea, because what we want to do is we want to be able to write code once, and even if you complain initially saying the code is not right, it doesn't work, but when you get it to work, it should work with no modifications on the following two cases. One is multi-core CPUs and the second is GPGPUs. So on this machine I have like 4 cores, right? And right now unless I do a little bit more work, I can't get Numba to really work on the cores. Similarly, if I want to run it on a GPU, I have to do a heck of a lot of more work to actually get it to work on a GPU. So what we want to do is we have a tool which actually imposes many of these restrictions on you, and which basically forces you to write your code in a manner that allows this to happen, which is you write your code once and it'll actually work out of the box pretty much on your multi-core machines. And now it's easy to get 16 core, 32 core machines very inexpensive. All right, so to do this we have to actually have several restrictions. The first is only NumPy arrays and basic primitives, which means your functions that are going to be optimized should not be doing creating Python objects or things like that. Okay? And we only handle contiguous arrays. This will probably change in some future point. We do not allow any NumPy or some SciPy functions being called from those functions, because that is usually a very big tripping point. And also no memory allocations or Python objects. So you can't create new arrays. All of those are not allowed. Okay. The instant you do that and you get your code to work, what this requires is for you to think or rethink your algorithm. Okay. And this is very important. And the instant you do that, you actually have a huge amount of benefits. So in my opinion, having those restrictions actually makes it very easy for someone to know, okay, these are the things I should do. If I do this, I'm kind of going to get good performance. Finally, we kind of force people to parallelize everything from the get-go. Okay, you can't parallelize certain things post-hoc. You have to do it when you start off. So to do this, we basically provide several primitives. One is called an element-wise operation. So which means if you have some operation that has to be repeated for every particle, you can basically wrap it up into an element-wise operation, and you write a simple function that tells you what to do for one element, and it will apply it automatically in parallel for you, whether it's on a multi-core machine or a multi-GPU or a single GPU machine. Okay, and as you know, GPUs have like the order of 2,500 or 2,000 cores. So it's very important that we use that hardware efficiently, and to use it efficiently, you actually have to write parallel code from the get-go. Okay. The second thing that you're going to need when you do something like this is you're going to need reductions, which is if I have like an array of values and we want to find the maximum or the minimum or the sum, all of these are called reductions. So just these two, that is map and reduce, actually allows you to do a lot. In fact, this is the famous map reduce paradigm. Okay, that's used element-wise and reduction operations. But it turns out this is not enough. In fact, I'm going to show you an example where it's not enough. The same example we're considering is not enough if you just do these two. You also need a scan. Okay, and scans, you can think of them as the equivalent of a parallel version of an algorithm that computes a cumulative sum. Okay, so think of a sum with all ones, all values of ones is basically going to add all of them up, accumulate it, and give you a new result. So scans are super useful because it turns out many algorithms can be written as a combination of either element-wise reductions or scans. A combination of these, you can actually write a huge number of algorithms, and that is why we provide these as primitives that work on both GPUs as well as on CPUs. Okay, so let's just take a quick look at element-wise operation just to understand better. So think about this simple function. Excuse me. You have a simple function ax plus b, classic example. You have x, y, a, b, and n as arrays that are passed in, and you want to just say for I in range n, just update this, set ya equal to this computation. Okay, so here notice this calculation is repeated for every particle. Okay, so you can convert this into a element wise in compile using the following. You just say def ax plus b, pass it the value I, the array, the index I, and then just do what you have to do inside this loop, and you simply wrap this up in a element wise kernel, and then you can just call this new element wise kernel and it will automatically parallelize it for you, so it will work everywhere. So it seems very simple, but this powerful abstraction allows us to do a lot of stuff. And what we'll do now is we'll take our existing example, and I'm going to now convert this to use compile and show you how easy it is to do, and let's see what we can do with this. Okay, so now what I'm going to do is I'm going to copy demo to demo compile. Now compile. Okay, so now I first do a bunch of imports. Compile.api, import annotate, element wise, and wrap. This will be clear very soon. I first annotate this, and now remember what I have to do for an element wise. I want to convert this into element wise operation. So I'm just going to remove this first guy, and then I'm going to just, okay, that's done. And now I do annotate, oops, annotate, I remove that, that's done, annotate, this, technically I don't need the argument n anymore, but I don't want to change the call signature, how the function is called, so I'm just going to ignore that. Okay, so now the next thing is, let's keep the linter happy. Okay, so the next thing we need to do is, remember what our goal is the following. Now I've made these element wise operations. I need to now wrap them as element wise. Right? So what I'm going to do is, I'm going to do that. I'm going to say compute force, or E compute force. It's an element wise compute force. Is element wise. Then E step 1. Now I could have done this, so many of you will be like, why on earth is this guy doing this? There's a method to my madness. I could have done this with a decorator, right? I didn't have to do this. The reason I'm doing this here is I can now control what backend gets used on demand, right? So if I did it before, I don't know the backend, right? And that makes it a little tricky. So I'm going to do it here. Let's see. So I can explicitly set the backend. That's all. Okay, I could in principle have used the all right. So now I just make this E compute force, E, BC. All of these are just to make it element-wise operations. I hope this is clear. So now there's only one thing to do. We have just made these element-wise operations. Now remember, I told you earlier that all of these are essentially being run, either could be run on a CPU or on a GPU. And we know that a GPU is a separate device. And essentially you've got to copy stuff from here, send it to the GPU, and the GPU is going to run some computations. Okay, so given that context, we probably need to take these NumPy arrays and push them somewhere or something like that. So what we do is we provide this little function called wrap, which allows you to wrap any NumPy arrays you're going to use. So I'm going to just call wrap. And what else? I think that is it. And finally, the reverse has to be done. So if it's running on a GPU, I need to do self.x.pull, which means I pull data from the CPU, from the GPU. Now this is not really necessary, but because I'm not going to be plotting this, but I want to just show you for completeness. Okay, and that's it. So now with this, in principle, I should just be able to run this. And hope that it works. Okay. So now, unlike Numba, so Numba goes through LLVM. Numba uses LLVM to basically, generate an IR that's essentially compiles it to machine code, and it's very fast at doing that. Whereas with compile, we actually generate low-level C, and that C is compiled. So it takes a bit more time for the compilation to happen. But once it's done, notice that it's really fast. In fact, it's actually faster than Numba for smaller arrays. Okay, so let me increase the number of elements to about, say, 5,000. Right? And it'll actually work with 5,000 and be really fast. Okay, and remember, the problem that we have implemented now is an n-squared problem, right? Because every particle is influenced by all other particles. So it's a really naive way of implementing it. So it's going to take a bit of time with 5,000. Maybe I shouldn't have given 5,000. But yeah, so now the thing is, I want to be able to do certain other things. I want to be able to say, possibly run it on a GPU, or I want to be able to run it, oh man, it takes too long. So I'm going to just maybe make it 2000. So it finishes in some reasonable amount of time. And now what I want to do is, as it does that, okay, so it takes about 5 seconds. If I run the same thing with Numba, let's see how long that takes. But in the meantime, compile also provides a simple argument parser, which gives us some default options. Okay, and notice it's neck and neck. As you increase the number of particles, Numba and compile will get closer and closer. Now, the current implementation is only serial, right? It turns out that without changing any code, I can either run this on a GPU or on all the 4 cores of the machine. So let's try doing that. So now if I do Python demo Numba, sorry, not Numba, compile. If I do -h, notice that I'll get a new number of options. I get this backend. I also can turn on OpenMP. Okay? I can also do some profiling, which is fine. We're not going to look at that. The rest are all options we already have. Right? So the fact that I did this actually gives us all of that. Okay, excuse me. So now I'm going to run OpenMP, and now it's going to actually have to recompile this, because it's going to run this on a, it has to recompile it so that it uses all my cores. And again, once I do this compilation, it's done. Okay, I don't have to revisit this computation. And now if I run it again, it's actually going to be faster, and it'll actually use all my cores. If you could see my CPU meter, you'll see all my cores starting to be used. And again, depending on how much work we have to do, this can run. If I increase the number of particles, I can actually saturate all of my CPUs. All right. So what we've done is we've actually taken this, and I actually ran this. We have this as a standard example. We've run this on the CPU with 4 cores again. So as you increase the number of particles, you see that essentially you get a speed up. This is the speed compared to running it on a single core. So if you have about 1000, you may at best get 3x. As you keep increasing this, the number of particles on the x-axis, the speed up that you get is close to like 5, or sort of saturates at around 5, telling you that you're actually able to use all your 4 cores. And doing this, you do for nothing extra. I don't have to change a single line of code. I simply turn on this flag --. Now if I had a GPU, my GPU on this machine is not quite working right now, but we also support OpenCL and CUDA. So which means on a Mac, if you have a reasonable GPU, you can actually say -b, so maybe let's just try this. I won't run it on the GPU, I'll run it on my CPU. I'm going to run it on the CPU. It'll actually work. It actually uses all my cores. It'll actually finish running this simulation. I don't know, about, yeah, in some amount of time. Okay, so the idea here is you can use OpenCL, and if you had CUDA, you can just run it, and I don't have to change a single line of code. And if you did this, in fact, we have a Colab notebook set up where you can create a GPU, or request a GPU, and run these codes and actually see how well it scales. And you see that if you run it on a P100 GPU, you actually get about 200x scale. Okay, this is huge. Alright, so now that we're done with this, what we're going to do now is I've shown you, like, just by doing a simple element wise, you're able to actually take code that works on one machine and can actually scale to many other, I can run it on a GPU and things like that. Okay, so one thing I didn't mention is, in actuality, I should have passed a backend, and I could explicitly set a backend. Here, I'm relying on it being automatically set. Okay, but that's all right. It doesn't matter. In principle, I could actually set an explicit backend and pass it everywhere I do a wrap. Alright, so now what we want to do is, we want to first observe that the previous implementation was order of n squared. Why? Because for every particle, I find the effect of all other particles. Okay? So if I want to do this in a more smart way, I clearly don't need to interact with all particles because some of them are very far away. They're more than 3 units away. So there's no point in actually looping over all of those guys. So a better version actually finds the neighbors. So given a point, it actually finds only a subset of the particles that are within a small distance and computes with them. Okay? Now doing this requires more features from compile, and I'll explain this very briefly. And secondly, we need to make sure that all the stuff we build is entirely parallel. Otherwise, it's not going to work on a GPG. Okay, so to this end, we implement what's commonly called as a nearest neighbor particle search algorithm. Okay, so let's see how to build this. Okay, I'm going to try and do a very quick version of explaining how this works. So the basic idea is to bin it. Okay, so imagine these green guys are all particles. Okay, and you're interested in the neighbors or to find the interactions on this particle, this red particle you see here. Clearly, if I scan only in these 9 boxes, right, then I can find all of these, provided this H is appropriately chosen, right? So if this H is 3 units, right, then clearly anything outside this blue highlighted box is no longer a neighbor. I don't need to worry about that. And here I've only shown 16 boxes, but in actuality you'll have like thousands of boxes, and you'll only be looking at 9 boxes at each time. So you significantly reduce the amount of computation. So again, for notation, I say I is in this direction, J is in this direction, this is 0, 0, and this is X max, Y max. Okay, and H is the bin size. Okay, and each of these are bins, these are all particles. Okay, so now let's look at an algorithm to actually do this. So first we fix a bin size H. I fix it as 3. Now what we need to do is we need to find a mapping from a given arbitrary point inside this box to an ij coordinate, so that given a point I can tell you which box it lies in. Okay, this is easy to do. You just do a floor of x by h and y by h to get I and j. But now we want to be able to do this in a single flattened one-dimensional array, okay, to make life easier. So what we do is, given an ij pair, you can flatten it to a single number, which is I times j max, where j max is the number of maximum j that you can have. Okay, I is this way, j is this way. All right. So which means if I were to count, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we have 16 boxes. Now that we have this, what we need to do is, for every particle, you find the bin ID. Okay, so if you take this particle, you find this bin. Okay, here it's 0, 1, 2, 3, 4, 5, 6. Okay, find that. Count the number of particles in each bin. Okay, so iterate over all the particles and find, okay, there are 2 here, 2 here, 2 here, so on and so forth. Doing this in parallel requires an atomic increment. Okay, and now when you're doing this, you also find whichth particle this particular incrementing particle is. All right. So when you add yourself to a particular box, you have to tell me where you are going to be added. Okay. So this is called a bin offset. So for that particle, okay, you basically set the count. That is how many fellows, at which point have I been added to this tuple. So what you're essentially going to do is, you're going to create a set of indices that tell me the actual part. You're going to create a one-dimensional array which tell me where, what are all the indices of the particles in each bin. Okay, that's what you're trying to do. Okay, so now once you have this, once you have the bin count, you can simply do a cumulative sum of the bin count, right? And that requires what's called a scan. Okay, that's a cumulative sum. So you can do this in parallel, and then that provides a starting location for each box, right? I'll explain this with an actual example, you'll understand it better. And then once you have the starting location, you need to set the actual indices in each box. Okay, so let's look at an example. So in pictures, it's much easier. So we have 9 boxes here, 0, 1, 2, all the black lettering denotes box numbers, 6, 7, 8. So there are 8 boxes. This is my H, and we have 9 particles in total. Okay, so I have 0, 1, 2, 3, 4, 5, all the way to 9. Okay, and here I have only 8 boxes. So these are all box, these 2 variables, bin count and start, are box specific. Okay, the others are particle specific. The bin offset, the PIDs, and the indices are essentially particle specific. Okay, so now what do? We iterate over every particle, and then we increment the count. So we first say, okay, let's pick the particle number 0. He lies in box number 1. Okay,
and it's in box number 1. So I go to the box number 1, this is this guy, I increment it by 1. Okay, when I increment it, at that time this is the first guy who's adding, because it's an atomic increment. I will now say my bin offset, this is the first particle, is 0 because there was nobody else. Okay, now the second particle in this box number, okay, so the second particle is now in cell number 0. Okay, so I say, oh, okay, now I go to this guy, increment this, I have 1, and again this is the only particle here. So the bin offset for the oh, I'm sorry, I should not do second particle. Second particle is 1. So let's look at the second particle. Second particle will be essentially this guy, will be 0. Okay, so if I look at particle number 1, that's the second particle, that's in box number 4. So I go to box number 4, increment it. This guy's bin offset is 0. Okay, sorry, 0. So bin offset is with respect to a particle. So let's repeat this. Let's pick particle number 5. Okay, so let's say 5 is picked. So 5 is in bin 4. So I go to 4. Now 1 has already put himself in. So the count would be 1, right? So the 5 particles bin offset, so go to 5, bin offset will be 1. Okay, and then yeah, so now this 4 now has 2, and I get the 7th guy, I get 3. So I have now found all the bin counts. So I do this for all particles, right? Then I do a cumulative sum and shift it by 1 to give me the start, which means the first fellow starts at 0. The second set of indices will start at 1, right? And since this guy has 2, the next box will start at 3. So this basically tells me the location in an array where I have to start looking for indices of particles in that dabba. Okay, so essentially I'm trying to flatten out this data structure. Okay, so I've told you how to do bin count, start, and bin offset. PIDs is simply, so let's pick a particle number 0. So particle number 0 is in box number 1. Particle number 1, right, particle number 1 is in bin number 4. Right, particle number 4, let's say, should be in box number 2. 4 should be in box number 2. Yes. All right. So this PID simply says, given a particle, which dabba is that particle. Okay. Now that I have gotten all this information, I can now set the actual indices. All right. So now I need to basically say that in box number 0 there is 2 guys. Right. So so let's go. Let's look at box number 4. Okay. Box number 4 has 3 particles. Okay, and its starting location is 4. So I go to indices, go to the 4th location, that's 1. So particle number 1, 5 and 7 exist in this double. Okay, so I hope you get the idea of how to do this. Okay, so given this, we need to implement this, and we need to use so now what we need to do is, given each particle I, we need to find its bin, find the neighboring particles, and for each neighbor bin, we iterate over the particles in the bin, okay, and get that and apply it in our calculations. Okay, so we'll now do a quick demo and look at the code for this. So okay, so what I've done here is I've again set up everything. I've set up all the element-wise stuff. And I've also set up all the NNPS related data structures. Okay, I've set up all of these objects. What we have to do is we have to just write this these set of functions. I don't know if we're going to have time to do this. I don't think we have enough time to do this. So I'm going to basically jump to the solution directly, and we'll just see what this looks like. So get ij is basically gives me the I and j for each particle. Given x, y, h, this will give me I and j. This converts this I and j to an actual number, which is a key, the actual box ID. Then we can find all the IDs. Okay, so this this function, for example, basically we declare we need an ij. We find the ij with get ij. Then we convert this to a box ID, right? And then we set the PIDs to this box ID. This particle, each particle, which dabba is it in? Let's just set here. We do an atomic increment and set the bin offset. Okay, so this is all those data structures we have talked about. Okay, so now let's look at how we use this. sorry, I'm going to rush through this. We first reset the neighbors, so we set the bin count to 0, because remember that's an atomic increment. We find the IDs, which does all the incrementing. We do a cumulative sum. This uses a scan, and this is also done in parallel. This is not just NumPy's sum. And then we get the pre-scan. We shift the cumulative sum by 1, starting at 0. So we just subtract the bin count so that we get the starting count. And then we call this set indices, which looks like this. Set indices basically just sets the indices back by computing the start location and the bin offset and setting that index interest. Right? So, a straightforward algorithm, and every step here is parallel. Yeah. Now, the only thing that needs to change is how do we compute the floors. So, what we do here is we find the box, then iterate over the neighboring boxes. Right? So, given a box, we know it's I and j. We look at I minus 1, I plus 1, j plus 1, j minus 1, and the Cartesian product of these. So, we get 9 boxes, okay, all the neighboring boxes. So, there's just a simple for loop for that. And now we need to make sure the box is actually a real box or it's an imaginary box. So, we shouldn't access an imaginary box. So, we just avoid those cases. And the rest of it is just the same old code. Okay? Nothing else changes. Okay, so straightforward. So, now if we run this, minus n, say 2000. This will be much faster, right? For 2000, that took seconds, right? So we can make this say 10,000. I've already compiled it before. So yeah, so for 10,000, it finished in 1.15 seconds because it's a much faster algorithm. In fact, let's run it for 20,000. Right? It will just take much less time. Okay, and also remember we're running it with OpenMP, so OpenMP is also going to start saturating all my codes. Okay, so I basically showed you the algorithm, and if you actually run this, you run both algorithms on a CPU, for example. This is the simple algorithm, n squared algorithm. Notice the slope is steeper. Okay. This is the linear algorithm, which is using the faster mechanism. And notice that even at less than like 30,000 particles, we get like 100-fold speed improvement, right? For just 30,000 particles. So this is like we get some really good results with this. So what I'm trying to say is, I'm just demonstrated to you how you can take a simple toy problem and actually extract enormous power from this. Okay, and with just pure Python code, right? So let's see how many lines of code. So it's 250 lines of code, right? We've actually taken a code that does plotting, that has parameters, that can be run on a GPU, that can be run on multi-core CPUs as well as in CPU. Okay, so that's pretty impressive. That's really what we're trying to shoot for. So under the covers, how does all this work? Well, what we do is we take this high-level Python code, and then we parse the AST, we generate low-level C code, okay, and we interface to Cython on the CPU. We interface to either PyOpenCL or PyCUDA to actually do the other, to use the GPUs and to use OpenCL as well. And the nice thing what we do is we try and provide a consistent interface. So now you're not, for each thing you have to write different code, is not the case, right? As I've demonstrated, that you can actually run the same exact code and extract performance from your hardware. So if you want to learn more, we have some reasonable documentation at compile.readthedocs.io. It's on GitHub, this project. Check it out. It still needs a lot more work and testing. For example, if you look at, if you run into a problem, the error messages are probably not going to be very helpful. We try, but there's a lot more work that needs to be done on that. Slices are not supported. Shouldn't be hard to add, but need some work. We don't support things like methods or objects. That's a little more involved, but we have ideas on how to do it, but it's just a lack of time. We need more math functionality. Basic math works, but probably need a lot more. Linear algebra and other tools also needs a lot more work, more optimizations. But I want to tell you that even though I've been saying we don't do X, Y, Z, this is actually something we use all the time for actual research projects, right? So the PySPH project where I showed you all those demonstrations, we actually do research now using the tools that we built. So it's not like a toy, it's actually usable today. So in summary, I want to show that, I just wanted to share with you that
you can do HPC with Python. It's very much possible, and you can extract good performance from today's hardware. I think it's worthwhile for most of us to learn some parallel programming, especially if you have to do low-level things like I do. Very often, you sit on top of frameworks that manage this for you. But if you're going to dive into this, I really suggest that you learn some parallel programming. And I submit that Compile is a powerful toolkit that you should check out. Before I end, I want to tell you that SciPy India is happening. It's on December 19th and 20th. Please register. It's an online conference again, so you don't have to travel or book tickets. Come here and register, and please join us. I'll stop here. So thank you very much once again. It's been a pleasure. I'm happy to take any questions. You can reach me on Twitter, or you can hit my website if you want to reach me. Thanks again.
Wow, that was really great. Thanks, Prabhu, for that session. And you guys, you can actually raise your hands for coming onto the stage as well, and you can ask your questions in Q&A, and then Prabhu will answer them for the next 10 minutes or 9 minutes. Feel free to use the raise
Hi,
hand
everyone.
feature. So guys, if you raise your hands, you can actually be brought onto the stage and you can actually talk to Prabhu. So if you have any questions, feel free to raise them. Prabhu, you're on mute.
Vijay, can you?
I think Prabhu's voice is. We can't hear you, Prabhu.
Shall I maybe?
Yeah.
Okay, I'll
Now,
shut off my video.
Yeah,
Okay,
yeah.
I'll shut off my video. That should make
Yeah.
it easier. Okay.
Yeah.
Yeah. So if you have a question, Bhaskar has raised his hand. I'm not sure what I'm supposed to.
Yeah. I'm sorry.
to
I'll.
get him on board. Yeah. Okay.
So thank you, Professor.
Okay. So Tabriz Khan has asked a question saying parallel programming. Any books to start with? It's a really good question actually. I have kind of assimilated this in bits and pieces. There are some good books on general scientific computing programming. I don't remember off the top of my head, but yeah, you can find. Google will do a much better job than I will. My general recommendation for books is don't just pick one, pick a few, and use the one that talks to you the best. So,
Professor, I have a simple question.
please.
I mean, when I usually see this distributed computing, I hear a lot about Spark. So Spark also does the same thing, right? It also distributes the task across multiple CPUs. So my naive question is like, why can't we use Spark for that? I mean, so what distinguish? I mean, what does the compile? How does it different from the Spark? Because nowadays Spark is also trying to offer to run the jobs on GPUs as well. So
Right.
I mean,
Right. Okay. So let me just set the context. I have not used Spark, but I have a very high level understanding of what many of these general tools tend to do. For example, there's not just Spark, there's also something called Dask, DASK.
right.
You may have heard of Dask. It's a really powerful framework. So I think if I treat both of them in the same class, I think my answer will apply in that case. So if you look at even Dask, if you're looking at high performance tasks like the one I'm talking about, we're doing a huge number of flops. Okay, and the idea here is we're trying to get as much out of the CPU as we can. And it's not something where it's a large, this huge amount of data that you're trying to churn through, which is usually the task where, you have something like Spark. There IO is very important. Here, it's like a smaller number of elements, and the amount of computation is extremely large. Okay, and so if you want to solve those kind of problems, you actually have to go down more to the to a lower level, and that's the reason we use things like OpenMP, things like that. Now, all of these other tools. So, for example, even if you're using Dask and you're trying to do an optimization, they will tell you to actually use Numba under the covers. So, if you want to do high performance computing of the kind that I'm talking about, they'll basically say, okay, use Numba and then distribute the Numba tasks to different CPUs. Right? That's the distributed aspect. It still doesn't address the actual local parallel computing. So, for example, even if you say, Spark is going to give me some performance on a GPU, ultimately someone has to take that and write a GPU kernel, which executes on a kernel. Okay. The rest of it is how do you, distribute these chunks of big tasks and ship it off to a GPU and things like that. So that is what Compile is in the business of. It's not in the task of the distribution. We have another distribution library which is based on NPI, but that's kind of irrelevant at this point. I hope that clarifies your question. It's like you use pure Python for C for that. Much higher level when you Spark. When you want to go lower level, you want to say I want to extract as much performance as from a single core. You're not going to say I'm going to distribute this. My original code that I wrote in pure Python. In principle, you could maybe distribute it with Spark with some work. So what we are trying to say is on this same machine, can I actually extract out more performance? So that's why it's fundamentally different from Spark.
Yeah.
That's why I couldn't quite answer that question when someone asked it on the chat.
Yeah, got it, bro, sir. Thank you.
Okay. Yeah. Okay. There's Bharani Kumar has a question, if we have time. Okay, so meanwhile, there's another. Have you using C for writing compile? Oh, okay. No, I'm not using C. It's all pure Python. We generate C and we compile that C. But the compile library itself is mostly pure Python.
Hi, hello, Professor. Am I audible?
Yes, Bhavani, you are audible.
Yeah, thank you. Professor, this is my question. I understand this is parallel computing, but how much it is compatible across multiple platforms or different hardware configuration? There can be quad-core, octa-core, or dual-core computers. So if you write in one computer, how much it will work on multiple other different computers or CPUs?
Thank you. That's a nice question, which I didn't quite answer. Yes, it will work with any number of cores. It will work on compile by itself. Should work on Windows. Should work on Mac OS, and it also works on Linux. Definitely, it works on Linux. The only thing is setting up the compiler. Sometimes is a bit of a headache if you're on Windows, but it's much easier nowadays. So yes, it should work, and it should scale to as many cores as you have. The problem is not compiled. The problem is your algorithm. So if your algorithm is poorly chosen, poorly written, you're in trouble. But if you write a nice algorithm which actually executes mostly in parallel, you can actually extract really good performance.
Okay, thank you.
Yeah, thank you. Okay, so any more questions?
I think Priyabrata has a question.
Sure.
On the feed.
Where is this? On the feed. Sorry, I wasn't checking the feed.
Yeah, I think it's.
Okay, yeah. So that's a great question. So in principle, it should work on the ARM if Cython works on the ARM. There is an issue currently with the 32-bit architecture that I'm trying to fix. I fixed it on the CPU end. I have to fix it on the OpenCL end. Just been a bit busy, so in a couple of weeks that should be fixed. So it does work on 32-bit as well as 64-bit. It should work on ARM, although I've not checked it out. And I think it does work on PPC 4LE. There's actually someone sent a PR to add continuous integration for PPC as well. So yeah, in principle, it's just generating C. So if C works on that platform, it should work. The harder thing is, of course, GPUs, but with CUDA and OpenCL, that makes it easier. And setting those up is also work. So there's that. Okay. Any more questions, Vijay?
I guess that's it. Prabhu, thanks a lot for answering the questions, and it was a very informative session.
Yeah, thank you so much. Yeah, thanks a lot. I have to worry
Thank you.
all the algorithmic
Yeah,
details.
I think the next session will start at 12.
Okay, thanks everyone. Bye-bye. Yes. Have a nice day. Enjoy your session, everyone. Nice meeting you all. Bye-bye.
Nice meeting you, Prabhu. Thank you.